Hi guys, how are you? I hope all is good. I'm just going to deliver another concept and some of the derivations and equations, primarily important for the understanding of free stream velocities, free stream flows with the help of Bernoulli's equation. And what we have actually earlier calculated is momentum and Euler theorem, and that too formulations help us to reach at this point, which is known as Bernoulli's equation. And we're going to actually calculate the free airspeed velocity as well in the second half of the video. And first of all, just talking the theory, talking the expressions, which are the algebraic expressions, and also talking about the some of the few understanding that needs to be done as far as the calculation of Bernoulli or Bernoulli equation is concerned. Bernoulli equation and free airspeed velocity calculation. Bernoulli equation is well known in fluid mechanics and relates the presence or relates the pressure to the velocity along a streamline in an inviscid incompressible flow. It was first formulated by Euler in 1700s. The derivation of this equation follows from Euler's equation using a fact that along the streamline, the velocity vector is tangential to the streamline. That is dx divided by x is equal to dy divided by v is equal to dz divided by w. First multiplying the equation, and this equation dv over change of time plus u into change of u by dx, and change of, we're going to represent v and w as well with respect to y and z, and that would be because taking the derivative and just equal to 1 minus rho, which is a change of rho by x through by dx, and then substitute equation this for v dx and w dx. Also, the first term of the equation will be set equal to 0. That is, at this time only steady flow will be considered. It's time, and that is also only the steady flow that will be considered. So what we're going to do, we're just going to take out this factor as in 0, and then we're going to actually consider the rest of the factors for our calculations. So similarly, we're going to apply the same concept when we're talking about with respect to v and with respect to y and z, talking about v and w. So that is why we have to take the same approach as we have taken, just dropping out the time factor, or actually taking it as 0. That is because at this time only steady flow will be considered. Okay, so you need to consider the steady flow in all points for for the fluid flowing through a given time. So for x dy, y dy, and u dz or v dz respectively, adding the three equations results in perfect differentials for p and v squared, v being the magnitude of the resultant velocity along the streamline. This last term results from the fact that this is derivative of u by x is equal to half derivative of u square by derivative of x, and v square is equal to x square plus v square plus w squared. Thus, along a streamline, Euler's equations become v into dv plus dp over rho is equal to 0. If rho is not a function of p, that is, a flow is incompressible, for example, equation this can be integrated immediately to give p plus half rho v square is equal to constant. If the flow is uniform, initially p plus half rho v square is equal to constant is equal to p by infinity plus half rho v infinity square. Here V is the magnitude of local velocity and P is the local static pressure. V infinity and P infinity are the corresponding free stream values. Equation is known as Bernoulli's equation. The counterpart to equation for compressible flow is obtained by assuming pressure and density changes to follow an isentropic process. For such a process, P by PR is equal to constant. R is the ratio of the specific heat at constant pressure to the specific heat at constant volume and is equal approx to 1.4 for air. Substituting this into equation and integrating leads to an equation sometimes referred to as the compressible Bernoulli's equation, which is in front of this. The equation can be written in forms of the acoustic velocity. First, it is necessary to derive the acoustic velocity, which can be done by the use of the momentum theorem and continuity. We have discussed it. Figure assumes what this figure assumes the possibility of a stationary disturbance in a steady flow, and across which the pressure, density, and velocity change by small increment. In the absence of body forces and viscosity, the momentum theorem gives this: minus dp is equal to p plus change of rho into u into or x plus d of x square minus rho of u square. And but from continuity we know that this is the form, and just taking out u change of rho is equal to minus rho into d of u, and u into d of rho is equal to minus rho into d of u. X square is equal to dp over d of rho. So this is how as u is equal to p into p and x plus du, and that is how p plus change of p into rho plus into change of rho. A stationary small disturbance, steady compressible flow. This is a stationary small disturbance in a steady compressible flow. If the small disturbance is stationary in the steady flow having a velocity of u, then obviously u is the velocity of the disturbance relative to the fluid. By definition, it follows that x given by equation is the acoustic velocity. By the use of equation this, the acoustic velocity is obtained as this. Okay, and an alternate form using the equation of equation of state is this, which you can use it this either this way. Equation can be written like this: the acoustic velocity is also included in figure for the standard atmospheric pressure, the standard atmospheric. So this is how the Bernoulli's equation has been related to in the form of compressible and in the form of incompressible form, and it's been related to the acoustic velocity, which can be actually also written in some of the forms as well when incorporated with the compressible Bernoulli's equation, and you can have all the assumptions in front of you. You just need to consider a steady stationary flows as disturbance, and when the disturbances occur with the velocity u obviously covering a distance x with the pressure p, and also the rho is the density. When there is all the when all these parameters are there, obviously there will be a displacement, there will be a distance covered by the fluid, by the pressure p in velocity u, so there will be also a change in, obviously you need to actually add in the density factor as well, just keeping it steady, a stationary small disturbance in a steady compressible flow. That is a stationary small disturbance in a steady compressible flow. That is how you're going to take it. X square is equal to dp into over d of rho. This is how it has to be done. So this is what we need to understand, and I hope that is enough for our understanding as a learner, and also as an application of this concept. When we talk about Bernoulli, we're definitely going to talk about this concept infrequently when we're talking about its applications, normally in the form of what? Normally in the form of research paper, normally in the form of thesis. Whenever you're going to go through, or any combination of professor, teacher, or the advisor, scholar combination of doing a thesis or research paper, or even attempting to complete some of the tasks which are related to his or her course of study, normally dealing with the PhD program. So for that reason, if there is some sort of confusion, if some sort of actually necessary things that we need to actually discuss, we're going to discuss, and that will help us to actually complete all the information. So this is the Bernoulli's equation and free air stream velocity calculation, and we have actually applied it with the help of the concepts of the momentum theorem, Euler's theorem, Euler's equation. So this is how we have derived, and we have reached out a form which is this incompressible flow, and that is how it has to be expressed. This is the form for the flow is for the incompressible flow, and for the compressible Bernoulli's equation would be this one. Okay, you just have to keep that in mind. These are the two different combinations of equations. So I hope that I have explained, but with the help of another interesting concept, which is acoustic velocity, we have actually explained the compressible Bernoulli's equation like this one. Okay, so this one has also been because of the acoustic velocity, we have actually replaced, and we have considered that we can also relate it in terms of acoustic velocity as well. And acoustic velocity is for the standing giving us the small example. When there is a stationary small disturbance in a steady compressible flow, there would be an acoustic velocity. Okay, and we have discussed what the acoustic velocity is by using the previous concept of momentum theorem and continuity, and we have discussed it. The disturbance, stationary disturbance in a steady flow across which the pressure, density, and velocity change by small increments. In the absence of body forces and viscosity, the momentum theorem gives this one. So this is how it has been done, and I hope that is enough for the explanation as far as the Bernoulli's equation is concerned. Now we're going to talk about the free stream velocity and the determination of free stream velocity at low speeds. We have done, by the way, some of the earlier concepts. We have talked about the V of velocity when we have talked about the calculation of A speed by using the Pittot's tube method, and of the A speed by the A speed indicator. We have done some part of the free stream velocity, but that was done in the form of calculation, or in the form incorporated in the theory specifically for that topic. And you can go and visit that video, and we can offer you to go through the same concept if you are interested in. But right now, what we are actually interested in is the determination of free stream velocity. So that is how we're going to do it at low speeds compared to the acoustic velocity, which we have already been discussed. A gas flow is essentially incompressible. Okay, incompressible in this case. And for a liquid equation applies if the fluid is brought to rest so that the local velocity is 0, then from equation the local pressure, referred to in this case as the stagnation or total pressure, is equal to the sum of the free stream static pressure P of infinity and P V of infinity squared by 2. This is how you're going to deal it. And thus a later term is called the dynamic pressure and is frequently denoted by the symbol Q, and thus V of infinity is equal to 2 P of P into minus P naught into P of infinity over rho, which is equal to 1 by 2, where P naught is the total pressure, also referred to as the stagnatic or reservoir pressure. This Q is normally known as the dynamic pressure. The pitot static tube known as this measures P naught minus P and is probably the most common means used to determine airspeed. Yes, however, notice that a 2.3 contains a mass density. This one contains the mass density that must be determined before the airspeed can be calculated. This is most readily achieved by measuring in addition to the difference between the stagnation pressure and the static pressure. That is what? P naught minus P of infinity, the static pressure itself and the temperature. The density is then determined from the equation of state at higher speed, and we will now examine what is high. Equation no longer holds, so that V of infinity, which is the free stream velocity, must be determined from equation which is this one. Okay, so at this point the subscript this has been dropped, so that pressure rho and V without a subscript may be local or free stream values, remembering that rho P over rho of pressure and over P is the square is a square of acoustic velocity. The preceding equation becomes this one, m squared by 2 plus 1 by rho minus 1 by rho minus 1 P naught by P, which is equal to rho over rho naught. And using equation this can be written as rho naught divided by rho, which is this. You just have to actually replace or just left hand side and right hand sides are actually changed over. The dynamic pressure Q is defined as this one, which can be written in terms of Mach number as this half 1 by 2 which is rho Pm squared. Combining this with equation 2.37 gives P naught minus P over Q is equal to 2R rho m squared, and which is equal to this. You just have to put on the values. The square root of equation is presented graphically in equation this one, which is theta is equal to 1 minus 0.2256 b. The departure of this function from unity is a measure of the error to be incurred in calculating the airspeed from the incompressible Bernoulli's equation. Below a Mach number of 0.5, the error is seen to be less than 3%. This is how you're going to deal with it when you are talking about the airspeed incorporated with the incompressible flow, and when we are talking about the dynamic pressure, you just have to correlate, and this is how you're going to use it when we are talking about the Bernoulli's equation. And the Bernoulli's equation can be used just by replacing it with the Mach number, and also Bernoulli's equation in terms of which is the compressible Bernoulli's equation in terms of acoustic velocity, when it would be used for the Mach numbers, and that would be that equation would become this one, and you can actually use this to further explain the dynamic pressure. Okay, ultimately going back again to the dynamic pressure and expressing this equation in terms of dynamic pressure, which you can relate like this. Okay, and that will help you to actually form an equation or the square root of an equation and present it graphically. Okay, with theta is equal to this. The departure of this function from unity is measure of the error to be incurred in calculating the airspeed from the incompressible Bernoulli's equation. So we just want to have that one. So considering the Mach number where is, that is also the prerequisite when we talk about the speed of air. So that is how, or the aircraft, you need to know the Mach number. So that is a very relative term when you're talking about the free airstream velocity in perspective to an aircraft, and also in perspective to the machinery. Obviously that is in our case is aircraft. So this equation normally help us to calculate. So the departure of this function from unity is a measure of the error to be incurred in calculating the air speed from the incompressible Bernoulli's equation below max. So this will help us to actually solve out the error. If there is any error in the airspeed, so this expression may help us to actually remove that error, and we can actually estimate as well that below the Mach number of 0.5, the error is seen to be less than 3%. So this is how it needs to be calculated. So I hope that is enough for the explanation. And if you need to know about any other further, because this expression which was at high speed, and we will now examine what is high equation, no longer holds, so that we must be determined from equation. Yes, for obviously free airstream velocity is for the highest stream, so that is why we are calculating the highest stream, so that is why we have removed this one. You can go through this whole lot of piece of information or the theory part, and you can well know about how you can get the information or remove an error for an airspeed at for an airspeed which normally is at high values. So obviously that may help you to actually, in presence of dynamic pressure, in presence of velocity, that may help you to actually calculate some of or remove some of the confusions. So I hope that I have explained enough, and if there is any sort of the confusion you want to have it, you can have in the comment section. We will definitely going to cover in our you can say industrial and project management channel, which normally covers the thesis. It will help us normally these lectures or these versions of actually delivering the topics will help us to actually cover some of the other advanced topics in terms of thesis, in terms of research papers. So we'll definitely going to cover the missing points, the missing links in those topics. So hope to see you in that channel. Till then, take care and have a nice day.